So let's start with a really big question. What if the entire universe, from the fleeting moment a particle exists all the way up to the complex reasoning of an AI, what if all of that is governed by just a few really simple rules of logic?
That is the ultimate question, isn't it? And here's the kicker. What if those rules aren't the clean black and white certainties of, old philosophy? The world of A is A, everything is either true or false.
Right. Not that simple.
Not at all. What if the real logic is the sprawling, messy, magnificent gray world of uncertainty, the world of probability?
And that's the central tension we really want to dive into today. We live in this era where we hear it constantly, that information is the new oil, that data is king.
Or drowning in it.
Exactly. We have terabytes of data flooding in. But you're suggesting that the data itself, the stream of stuff we collect, the specific outcomes, the information, that might actually just be the noise.
It's the smoke, not the fire. The data is just the messy byproduct of a much deeper, much more elegant engine. The real power, the actual deep knowledge, isn't in the data points themselves. It's in the compressed, the invariant, the fundamental rules, the mathematical logic that generates all that data in the first place.
Okay, hang on. Let's unpack that, because that's a genuinely profound shift in perspective.
Yeah.
You're saying the rules are more important than the results.
Precisely. And this isn't just some abstract philosophical debate we're having. This is the operational secret behind basically every complex system that drives modern science and technology. I mean, whether we're talking about the math that predicts the bizarre behavior of quantum particles or the statistical frameworks that are driving the latest AI breakthroughs.
They're all using the same playbook.
They all adhere to the same foundational logic of chance.
And to give you, our listeners, a bit of context, we've been sort of circling this topic for a while. In a previous deep dive, we explored the idea of the value function, which is this abstract way we quantify utility and, find the signal in the noise to make the best possible decisions. That episode was about how to use uncertainty.
And we'll definitely leave a link to that in the description below. It's a good primer.
Absolutely.
But today, we're going a layer deeper. We're tackling the foundational structure underneath that value function. We're exploring how humanity went from trying to calculate the odds at a dice table to defining this incredibly rigorous mathematical framework for handling uncertainty itself. Our mission today is to dive into the foundational structure of chance. These few simple abstract rules, the axioms, laid down by the brilliant Russian mathematician Andrey Kolmogorov back in 1933.
So this is a mission to explore how those abstract rules manage to bridge the gap between pure mathematics and the physical, unpredictable world we actually live in. It's an incredible story when you think about it. Probability literally started with gamblers trying to outwit chance.
And it ended up becoming the most rigorous foundation of our reality. It went from a collection of street-smart tricks to this robust mathematical framework because we finally decided that chance wasn't some, inscrutable divine act. It was something that could be measured, rigorously modeled, and most importantly, universally understood.
And we are just so grateful to you, our listeners, for joining us on this quest. We're seeing a ton of engagement for the show, and it's so clear that you're as fascinated by these deep dives as we are. Your support just proves that there's a real space for this kind of deep, rigorous research outside of the usual campus lecture hall.
We truly appreciate that engagement. It means a lot.
And speaking of engagement, if you enjoy these detailed discussions and you want to ensure we can keep producing this kind of deep research and start creating high-quality video formats, we really do need your help. We're trying to unlock funding for a new video editing project we're calling the Mosaic AI Video Editor. And to get that started, we need to hit 1,000 subscribers across all platforms. So please, if you're enjoying this, just take a quick moment to subscribe on YouTube Music, Spotify, Apple Podcasts, or wherever you're listening. Makes a huge difference. I'm Satosha.
And I'm Satoshi.
Okay.
Now let's jump in. Let's break down how this logic of science was discovered, starting in the smoky back rooms of 17th century Europe.
When we talk about probability, it feels like it's always been around, but the mathematical treatment of it is surprisingly modern, isn't it? Yeah. Games of chance have existed for millennia. People were using those little knuckle bones, the astragalus.
Yeah, for thousands of years. But often for divination, for asking the fates for guidance. And that's the crucial point. For centuries, random outcomes were seen as divine providence, the will of the gods or the fates. So the philosophical barrier to actually analyzing it with math was enormous.
If a god is determining the roll of the dice, trying to calculate it is kind of blasphemous.
Or just futile. The whole modern concept required a huge philosophical shift, accepting that uncertainty is inherent in the world, but it's also manageable.
And the first person to even start to formally write this down, even though his work was ignored for a century, was Girolamo Cardano in the 16th century.
Cardano was a legendary figure, a brilliant polymath, a physician, but also a compulsive gambler. I mean, he often squandered his own wealth at the tables. He wrote this book, Liber du Luder Allié, the book on games of chance, but it wasn't published until after he died. And in it, he gives us the very first definition of probability as a simple ratio, the number of favorable outcomes divided by the total number of possible outcomes.
So super basic, but he recognized the symmetry of chance, that a fair die treats all 6 of its sides equally.
It was crude, but it was the start of formal frequency-based thinking.
But the real spark, the intellectual ignition, came about a century later with a French nobleman, the Chevalier de Marais. He was basically getting frustrated because his street smarts were failing him at the gaming tables.
Exactly. De Marais wasn't a mathematician, but he was a keen observer of patterns, and his confusion led to the famous correspondence that really birthed modern probability theory. His dice problem is the perfect example of how human intuition just completely falls apart when you're faced with compounding uncertainty.
Walk us through his mistake, because I think this really helps us get the nonlinear nature of chance.
Okay, so de Marais knew from long experience that if he bet on getting at least 1/6 foot in 4 rolls of a single die, he usually won. The actual probability of success there is about 51.77%, so he was making money.
He had a profitable system.
Right, so he tried to scale it up. He reasoned that since a pair of dice has 36 possible outcomes, which is 6 times more than a single die, he should just need 6 times as many rolls to get a similar edge.
So he was betting on getting at least one double 6 in 24 rolls. 4 rolls times 6.
Exactly. The logic seems plausible on the surface, but he kept losing money, and he couldn't figure out why. The reason is that the correct way to calculate it is to use the complement rule. You figure out the chance of not getting the outcome and then subtract that from 100%.
And the chance of not getting a double 6 in a single roll is 35 out of 36.
Right. And for 24 independent rolls, you have to multiply that fraction by itself 24 times. 35 over 36 to the power of 24. That comes out to about a 50.85% chance of failure, which means his chance of success was only 49.15%.
He was betting on a losing proposition without even realizing it.
And it demonstrated that probability doesn't scale linearly. It scales exponentially because each independent event multiplies the previous uncertainty. This nonlinear reality just defied centuries of common sense.
That's fascinating. That multiplication rule is so intuitive to us now, but at the time it was a profound realization. And his second problem, the problem of points, was even harder because it was about predicting the value of events that hadn't happened yet.
The problem of points was an ancient challenge. How do you fairly divide the stakes if a game, let's say, first to 3 wins, gets interrupted when the score is, say, 2-1? You can't just split the pot 2-1 based on the current score. That's unfair because the player who only needs 1 more point to win has a much, much higher future expectation.
And this question is what led to the famous correspondence in 1654 between Blaise Pascal and Pierre de Fermat. They solved it, and in the process, they basically created the framework for modern probability theory.
And what's remarkable is that they both got the right answer using 2 totally different but complementary methods. Fermat used what we call the combinatorial method. He defined the sample space by imagining the game continuing for the maximum number of rounds it could possibly take. Then he just rigorously listed every single possible sequence of wins and losses in those future rounds.
So if player A needed 1 point and player B needed 2, Fermat would list out all 4 possible outcomes over the next 2 hypothetical rounds.
Correct. And by simply counting how many of those possible worlds led to a win for player A versus player B, he found the exact fair ratio for splitting the stakes. It was a rigorous counting exercise.
But Pascal found that process a bit tedious, especially for longer games, and that tedium led him to his truly groundbreaking idea, the method of expectations, or what we now call backward induction.
Pascal don't care about listing every possible future. He reasoned recursively, he looked at any state of the game, like the 2-1 score, and said, the current value of the game to player A is just the average of the 2 possible states that could come next. The value if they win the next round and the value if they lose the next round. He just worked backward from the end of the game where the outcomes were certain.
And this recursive averaging introduced the concept of mathematical expectation. This is where the whole field really pivots from just being gambling tricks to serious mathematics.
Mathematical expectation, the weighted average of all possible future outcomes, is the very definition of rational choice under uncertainty. It's what guides decision theory in high finance, it's the basis for the entire insurance industry, and critically, it is the cornerstone of reinforcement learning in modern AI. An AI agent deciding its next move is literally calculating the mathematical expectation of future rewards, using Pascal's logic from 1654.
So by the 18th century, the field had some real rigor. You get Jacob Bernoulli establishing the law of large numbers in 1713, which provides that first crucial bridge connecting an abstract number, a probability, to physical reality.
Right. Bernoulli showed that if you repeat a trial enough times, the observed results must converge to the theoretical probability. It grounds the abstract math in the measurable world. Then you have Abraham de Moivre, who was trying to calculate these things for huge numbers of trials, and in 1718 he discovers the inevitable shape that emerges, the bell curve, the normal distribution. That brought calculus into the field.
And then Pierre-Simon Laplace synthesizes it all in 1812, extending probability to massive domains like astronomy and jurisprudence.
Laplace gave us the definitive classical definition. The ratio of favorable cases to all possible cases. It was a monumental achievement. But it had a fatal logical flaw that mathematicians couldn't just ignore.
Colourability.
Exactly. The definition requires the possible cases to be equally possible. But how do you define equally possible without already having a working definition of probability? You can't.
You're trapped in a loop.
You're defining the concept using the concept itself. For pure mathematicians who wanted the same kind of rigor as geometry, this was completely unacceptable. If the foundation was circular, the whole intellectual building was unsound.
So by the late 19th century, probability was kind of intellectually adrift. It had this circularity problem. And then the rise of formal set theory started introducing all these paradoxes that just exposed how shaky the foundations really were.
And the most famous example of this, the one that proved that physical intuition was just utterly insufficient, was Bertrand's paradox from 1889.
It's a beautiful thought experiment. It just demolished the idea that the word random has some kind of innate, objective, physical meaning.
It's so simple. Imagine a circle. And you want to find the probability that a random chord, a line segment inside the circle, is longer than the side of an equilateral triangle drawn inside that same circle.
Okay, my first instinct, and I think most people's, is that there has to be one single objective answer to that question.
But there isn't. And that's the paradox. The answer depends entirely on how you physically define the process of drawing the chord.
Yeah.
If you define the chord by picking two random points on the circumference and connecting them, the probability that the chord is longer is 1/3.
Okay.
But if you define the chord by picking a random radius and then picking a random point on that radius to be the chord's midpoint, the probability is 1/2.
A completely different answer.
And there's a third way. If you choose the chord by picking a random midpoint anywhere inside the circle's area, the probability is 1/4. 3 mathematically valid methods, 3 totally different probabilities.
That's just devastating to the classical view. It proves that the outcome is completely tied to the process of measurement. You can't separate them.
The paradox proved that probability couldn't just be derived from intuition or by counting outcomes. It needed a rigorous, abstract structure defined before you even start calculating. It needed a new kind of math that could handle things you can't count, like the infinite number of points on a line.
And this is where Andrey Kolmogorov comes in, providing the necessary mathematical plumbing in 1933.
Kolmogorov's genius was twofold. First, he just completely ignored the philosophical arguments about what probability is. He didn't care if it was a frequency or a belief. And second, he treated probability as a purely abstract branch of measure theory.
Measure theory sounds incredibly academic. How can we make that accessible for everyone?
Think of measure theory as the rigorous mathematics of area and size, but for abstract spaces. It asks, how do you assign a consistent size or measure to a collection of points, even an infinite one? Kolmogorov took this framework and created what's called a probability space. It's an abstract triplet. You have the set of all possible outcomes, which is the sample space. Then you have the collection of events you're allowed to measure, the event space. And finally, the probability measure itself, which is the function that maps those events to a number between 0 and 1.
So this framework forces you, the user, to specify exactly how you're measuring things before you even start. It solves Bertrand's paradox instantly. You can't just say a random chord. You have to define the sample space in the measure.
Precisely. And the entire system, the logic of all of modern science, is governed by just three simple, universal, and elegant axioms that come from this foundation.
Let's break down these pillars. The first one is the most intuitive. Axiom 1, non-negativity. The probability of any event has to be greater than or equal to 0.
This anchors probability to the logic of existence. A probability measures the potential for something to happen. It can't be negative. You can't have a negative chance of finding a coin. It either happens, which is a positive chance, or it doesn't, which is a 0 chance. It's simple, but it's the first guardrail against mathematical nonsense.
Okay, then axiom 2 is normalization. The probability of the entire sample space, so all possible outcomes taken together, is exactly 1.
This is the axiom of certainty. It means possibility is conserved. Something must happen. If the total probability of everything was less than 1, it would imply there's a hole in reality where nothing occurs, which is logically impossible. It ensures our models account for everything and gives us that universal 0 to 1 scale.
And the third axiom, the one that does all the heavy lifting for modern physics and calculus, is countable additivity. This says that if you have a sequence of events that can't happen at the same time, they're mutually exclusive, the chance of any one of them happening is just the sum of their individual chances.
This is the critical one. The countable part of the name is key because it lets the sum rule extend to an infinite sequence of events. Why does that matter? Think about throwing a dart at a dartboard. The probability of hitting any single specific point on the board is 0.
Because there's an infinite number of points.
An infinite number, but the probability of hitting the entire board, the area, is 1. So we have to be able to sum up an infinite number of events, each with 0 probability, and still get a positive, finite probability for the larger area.
That's the magic trick.
It is. Without countable additivity, you can't build the bridge between discrete counting, like with dice, and continuous integration, the calculus you need to model flowing water or electricity or particle distributions. It's the mathematical engine that makes modern science possible.
So Kolmogorov gave us the unassailable mathematical syntax, the structure.
Yeah.
But the philosophical question was still there. Why these rules? Why is probability the correct logic for science? And this is where E.T. Jaynes comes in, arguing that probability isn't just a tool, it's extended logic.
Jaynes was a towering figure in physics and statistics, and his work, Probability Theory. The logic of science makes this profound argument that probability theory is the unique, consistent set of rules for reasoning when your information is incomplete. In other words, when you're uncertain.
So he's saying that just as Aristotelian logic governs certainty, probability governs uncertainty. How did he prove that it's the only way to do this consistently?
He used a powerful thought experiment. He said, let's design an imaginary reasoning robot. It has to process information and form logical degrees of belief about the world. But we're not going to program in the rules of probability. We're only going to impose a few simple, common sense requirements on its reasoning process.
Okay, what were those requirements?
3 main things. First, plausibility has to be represented by a real number, a degree of belief between 0 and 1. Second, just common sense. If the robot gets new evidence that supports an idea, its belief in that idea can't go down. And third, the most critical one, consistency. If the robot can reach the same conclusion through 2 different logical paths, the numerical result at the end has to be identical. Its reasoning must be path independent.
That seems like the bare minimum for rationality.
It is, and the profound mathematical finding, formalized by R.T. Cox in the 1940s, it's known as Cox's theorem, showed that any system that satisfies these simple logical requirements must operate according to the rules of probability, specifically the rules of Bayesian theory.
Wait, let me make sure I'm getting the gravity of this. You're saying that if an advanced alien civilization exists and it uses logic to reason under uncertainty, it has to be using probability theory, whether it calls it that or not.
That is the implication. Probability theory seems to be baked into rationality itself. Any deviation from these axioms will eventually lead to logical contradictions. Or it makes you vulnerable to what statisticians call a Dutch book, where you can be tricked into a series of bets that guarantees you lose money no matter what happens. Probability is the only way to avoid that logical vulnerability.
That's powerful. But let's circle back to Kolmogorov's third axiom, countable additivity, because that one is still the subject of some serious philosophical debate, especially around the idea of infinity.
Right. This is where pure mathematicians can clash with philosophers and even some applied scientists. The core objection is this. If the physical universe is finite, it's discrete at the Planck scale, and it's bounded in its total information content, then why do we need an axiom that dictates how we handle infinite sequences of events? It seems like a mathematical convenience, not a physical necessity.
And the most famous counterexample to this was proposed by the Italian probabilist Bruno Di Finetti.
De Finetti's argument uses this powerful image of the infinite lottery. Imagine a conceptual lottery where you have to pick a single number from the set of all natural numbers. 1, 2, 3, on to infinity. De Finetti argued that you should be indifferent among all those numbers. They should all have an equal probability of being chosen.
But if every number has an equal chance, what can that chance possibly be?
This is where Kolmogorov's axioms break down. If the probability of picking any single number is 0, then by countable additivity, the sum of all those zeros is 0. This violates axiom 2, normalization, which demands the sum of all possibilities must be 1. You have a universe where the probability of picking something is 0.
And if the probability is anything greater than 0, no matter how tiny,
the sum of infinitely many positive numbers just blows up to infinity, again, violating the normalization axiom. So De Finetti said, since we can rationally conceive of this kind of lottery, Kolmogorov's reliance on infinity must be flawed for describing reality.
So how do we reconcile this? Why did the mathematical community stick with countable additivity?
The resolution is really practical. Countable additivity is a necessary tool for doing idealized physics. While the real world is discrete and finite, the mathematical models we use to describe it, calculus, the real number line, continuous fields, are continuous and infinite. To use the incredibly powerful tools of integration and differential equations, we need axiom 3.
So it's the functional bridge that forces our continuous models to behave like the discrete reality they're trying to describe.
Exactly. It mandates that probability mass has to be localized and eventually decay to 0, like the long tails of the bell curve dropping off. This matches the physical observation that matter and energy are localized and finite. It lets us approximate astronomical numbers of discrete particles, like gas molecules, as smooth, continuous fields, which is the only way to make the physics tractable. It's the price we pay to use the powerful language of calculus.
So if Kolmogorov's axioms are the foundational rules, then the normal distribution, the bell curve, is the most recognizable signature of those rules printed onto the physical world. It shows up absolutely everywhere. Human height, measurement errors, noise in circuits. Why is it so ubiquitous?
The bell curve is not an accident. It is a mathematical inevitability dictated by the most powerful statistical result of all time, the central limit theorem, or CLT.
We need to give the CLT the explanation it deserves. What is its core function?
Simply put, the theorem states that if you take the sum or the average of a large number of independent random variables, the resulting distribution will always converge toward a normal distribution. And this is the amazing part. It happens regardless of the shape of the original distributions you started with. You can sum up a collection of wildly skewed, bizarre distributions, and the sum will still look like a bell curve.
Let's use a concrete example, like human height, to make that clear.
Yeah. Human height is the perfect example. It's not determined by a single gene or one environmental factor. It's the aggregate result of thousands of small independent effects. Tens of thousands of genetic variants, plus thousands of tiny environmental factors, childhood nutrition, sleep patterns, you name it. Each of these factors contributes a small, random push or pull to the final outcome.
So the CLT says that when you combine all those thousands of small, independent random factors, the distribution of heights across a large population must result in that predictable bell curve shape.
And that's profound. It means the individual factors can be completely chaotic or non-normal, but the aggregate of the system is rigidly predictable. The same mechanism applies to measurement error in any scientific experiment. The final reading is the sum of countless tiny independent thermal fluctuations, atmospheric noise, voltage drifts. The sum of all that noise is always Gaussian.
And from an information theory perspective, the normal distribution also has this unique status as the state of maximum entropy.
Right. Maximum entropy in this context just means it represents the state of maximum statistical disorder or ignorance that's still consistent with what we know. If you only know the average height and the spread of the data, the most unbiased, honest assumption you can make about the shape of the rest of the data is that it follows a bell curve. Nature, it seems, just defaults to this mathematically mandated state of maximum statistical disorder.
And this inherent link between probability, entropy, and disorder brings us to the other monumental victory of probability in physics, the derivation of thermodynamics, the laws of heat by James Clerk Maxwell and Ludwig Boltzmann.
This was a revolutionary conceptual leap. Before them, temperature and pressure were treated as fundamental forces. Maxwell and Boltzmann realized they were just statistical averages. They derived the universal laws of heat not from classical mechanics, but from combinatorics and probability. This created the entire field of statistical mechanics.
How did they manage to derive the rules of heat just from counting?
They started with the assumption that every possible microstate, every single arrangement of the positions and energies of the particles in a gas, is equally likely. Their central task was to calculate the number of ways, which they symbolized with a dollar, that the particles could arrange themselves to produce a specific macroscopic state, like a certain temperature or pressure.
So the state we actually observe, a pot of boiling water at 100 degrees Celsius, is simply the arrangement that corresponds to the largest number of underlying microscopic possibilities.
The vastest number, by far. When you maximize the dollars, the number of ways, you are maximizing the system's entropy. Boltzmann famously showed that entropy is directly related to the logarithm of dollars, and by maximizing this, he derived the Maxwell-Boltzmann distribution, which defines the probability of a particle having a certain amount of energy.
And what's the incredible insight that comes out when you apply this logic to heat?
It fundamentally redefines what temperature, tollers, is. Temperature is not a fundamental quantity like mass or charge. It emerges as a statistical parameter, a measure of the average kinetic energy from the probability distribution of all the particles. The universal laws of thermodynamics, including the irreversible march toward disorder, are simply the laws of large numbers applied to an astronomical number of atoms. The logic of chance governs the flow of heat and the ultimate fate of the universe.
That transition from statistical mechanics brings us to the most radical philosophical shift of all, the advent of quantum mechanics. Before QM, probability was epistemic. It reflected our ignorance. A particle was definitely somewhere, we just didn't know where.
But in quantum mechanics, probability became ontological. It started to reflect the fundamental nature of reality itself. The probability isn't in our head anymore, it's in the structure of the universe. The particle exists in the state of potentiality, defined only by a probability distribution until it's measured.
And the mathematical bridge connecting that abstract quantum state, the wave function, to the observable physical world is the Born rule, which Max Born postulated in 1926.
The Born rule is the linchpin of quantum theory. It tells us that the probability of measuring a quantum system in a specific state is proportional to the square of the amplitude of its wave function. It's the rule that turns an abstract, complex number into a real-world, measurable probability.
But to a skeptic, that rule could seem arbitrary. Was it just a guess that happened to work, or is there a deep mathematical justification for that squaring operation?
That's the debate that's driven quantum foundations for nearly a century, and the answer is incredibly rigorous. There's a theorem, Gleason's theorem, which proves that for quantum systems in spaces with more than 2 dimensions, the Born rule is the only consistent probability measure possible on the abstract mathematical structure of quantum reality.
So just like Cox's theorem showed that probability is the only consistent logic for rational agents, Gleason's theorem shows the Born rule is the only consistent probability measure for quantum systems.
It gives the Born rule an almost axiomatic certainty, just like Kolmogorov's rules, but it's tailored to the specific geometry of the quantum world. However, understanding what that probability means is still fiercely debated. If probability is fundamental, what does that imply about the nature of existence?
It leads to these wild interpretations, like the many worlds interpretation, where every possible outcome actually happens in a constantly branching universe. But if every branch is realized, how can probability even be meaningful?
It's a deep conceptual challenge for MWI. If you, the observer, split into 2 copies, one seeing result A and one seeing result B, what does the probability of A even mean? MWI theorists, like David Deutsch, recover the Born rule not from physics, but from decision theory. They argue that even in a branching universe, a rational agent must still bet and make decisions according to the Born rule to maximize their expected utility across all future branches.
So is probability recovered from the logic of rational action, not from mechanics?
Exactly. And on the complete opposite end of the spectrum, you have quantum Bayesianism, or cubism. It takes the Keynesian view probability as extended logic and applies it to quantum reality. Cubism says the quantum state isn't a description of the world itself, but the observer's belief about the world. It treats the Born rule as the extension of logical consistency into the quantum realm.
In all these cases, whether it's the physics, the decision theory, or the philosophy, probability remains the essential, non-negotiable logic that bridges the abstract description of reality and the empirical results we see. So let's fast forward to today, because everything we've just talked about, the axioms, the statistical distributions, it all converges in the engine room of the current AI revolution. A generative AI is fundamentally a Kolmogorov machine. It's built on probability theory at a scale we've never seen before.
That is the crucial point. When you interact with a large language model, asking it to write an email or summarize a topic, it is fundamentally a prediction engine. It is estimating the conditional probability of the next token, which is usually a word or part of a word, given the sequence of all the preceding tokens.
So it's not creating in the human sense. It's making a series of incredibly complex, high-stakes, probabilistic guesses. It's just saying, given that I've seen the quick brown fox jumped over the highest probability next word is lazy, then maybe fence, then log.
It knows patterns of co-occurrence, not facts or causation. When it chooses a word, it's because that word had one of the highest raw probability scores, or logits, following the input sequence. The intelligence emerges from the sheer complexity of the probabilistic landscape it can model.
But the truly fascinating part is that we, the users, can actually dial the knob on that randomness. We can control the creativity of its guesses using sampling parameters. The most common one is the temperature setting.
And temperature is a direct borrowing from statistical mechanics, from the Maxwell-Boltzmann distribution we talked about. In AI, temperature scales those raw probability scores. When you set a high temperature, you flatten the probability distribution. You increase the system's statistical entropy.
Which means that words with slightly lower probabilities suddenly become much more likely to be picked.
Precisely. This increases randomness, generating more creative, unexpected, even chaotic output. It raises the chance of a hallucination, a statistically unlikely but grammatically plausible statement. Conversely, a low temperature sharpens the distribution, suppressing those less likely words and forcing the model to stick to the most probable, most deterministic phrases.
Right. Low temperature for code generation, high temperature for brainstorming poetry. But there are even more sophisticated methods like nucleus sampling or top-up. How does that connect back to Kolmogorov?
Top is a brilliant application of the axioms. Instead of using a fixed set of possibilities, the model dynamically calculates the probability of all possible next words. It then orders them by probability and starts summing the probabilities of the most likely words until that sum reaches a specific threshold, say 90%.
So if the model is very confident and 90% of the probability is concentrated in the top 3 words, it only considers those 3. But if it's uncertain that 90% is spread across 50 words,
it samples from all 50, and this is a direct practical application of Kolmogorov's normalization axiom. The axiom says the total probability mass must equal 1. By forcing the selection set to sum up to our threshold, we are controlling the output based on probability conservation. It uses the foundation of logic to balance diversity and coherence.
That's amazing. And this probabilistic chaos is even more explicit in generative art models like Stable Diffusion. They're literally trying to reverse the process of chaos itself.
They are. They're applying the laws of statistical mechanics to visual data. The models are trained on 2 processes. The forward process simulates the physical world by gradually adding Gaussian noise-pure, normal distribution static to an image over hundreds of steps. It's just adding entropy.
And the reverse process is the AI learning to undo that noise step by step to predict the original image.
The AI is learning the probability distribution of what an image looks like when you remove noise. This reversal is modeled using Langevin dynamics, the same mathematics used in 1908 to describe Brownian motion, the random jittering of pollen particles in water. The AI is using the physics of random motion to condense visual order out of pure chaos.
It's statistical physics applied to pixels. And finally, the training of these massive networks relies on randomness through stochastic gradient descent, or SGD.
SGD is the core method for learning. Computing the true gradient, the optimal direction to adjust weights over terabytes of data, is impossible. So the algorithm estimates it using small, random batches of data. That's why it's stochastic.
But wouldn't a random, imperfect estimate slow down the learning?
That's the crucial insight. The randomness is a feature, not a bug. While the random gradient is imperfect, its expected value is the true gradient. More importantly, the noise introduced by the random sampling actually helps the algorithm escape problematic areas in the optimization landscape. It makes the learning more robust, faster, and helps it generalize better to new data. Probability and noise are essential for the intelligence itself to emerge.
Okay, so let's formalize a distinction we started with at the very beginning. The difference between knowledge and information, using the precise language we've now established.
Right. Information is the realization. It's the specific historical path taken, the noise, the actual sequence of heads and tails you saw. It's high entropy, a detailed record. And because a single sequence doesn't capture the underlying law, it's often lossy when it comes to the truth.
And knowledge.
Knowledge is the probability measure itself. It's the invariant self, the signal. It's the compressed underlying algorithm like saying the probability of heads is 0.5. Knowledge is lossless because it describes the potential of all possible paths. Knowledge is the rule set, information is the output.
This dichotomy helps us understand that ancient philosophical paradox of the one versus the many. How does a single, unified system knowledge decentralize into infinite variety information?
The mechanism is a mathematical concept called infinite divisibility. A probability distribution is infinitely divisible if it can be represented as the sum of any number of independent, identically distributed random variables. It mirrors decentralization perfectly.
Meaning the structure of the whole is reflected in the properties of every part.
Exactly. The normal distribution is the primary example. If you slice a bell curve, the slices are still scaled bell curves. The properties of the whole are encoded into the parts. This is how the single unified law, the knowledge, decentralizes into infinite variety.
But no matter how much decentralization happens, the system stays unified because of Kolmogorov's normalization axiom.
That's the conservation law of existence. No matter how infinitely diverse the manifest world becomes, the total probability mass, the sum of all possibility, must always equal exactly 1. The infinite variety of the world is just a decentralized, infinitely divisible expression of a single, unified probability measure. And the bell curve is the signature of this law in action.
This profound connection brings us to a crucial societal point. If probability is the logic of science, AI, and reality itself, why is it so often pushed to the side in high school curricula in favor of calculus?
This is often called the calculus trap. Calculus is essential for niche fields like physics and high-level engineering, but probability and statistics are essential for universal literacy and citizenship. Every voter has to interpret polling data with margins of error. Every patient has to interpret medical tests with false positives.
The functional utility of statistical literacy for just navigating the modern world far outweighs the utility of calculating the volume of a weirdly shaped object.
And beyond that, research by pioneers like Kahneman and Tversky revealed that humans suffer from systematic, innate cognitive biases when dealing with uncertainty. We are hardwired to misunderstand chance. Things like base rate neglect, where we ignore the general prevalence of something, or the conjunction fallacy, where we think specific conditions are more probable than general ones.
We're just fundamentally flawed, intuitive statisticians.
We are. And formal probability education is the way we equip you, the listener, with the cognitive tools to overcome these innate biases. It makes you less susceptible to manipulation by misleading statistics in the media, in politics, and marketing. It's an ethical imperative of modern education.
So finally, where does probability as a discipline even fit? Is it pure math? Is it an empirical science?
It occupies this unique, essential superposition. Its axiomatic core is pure mathematics, rooted in measure theory. Its applications, statistics, is empirical science. It deals with data. And its models are scientific hypotheses that have to be validated. And its interpretive logic, Bayesianism, is a branch of philosophy.
It's the single, indispensable bridge. It connects the abstract world of logic and analysis to the noisy, unpredictable world of data and physics. It is, in the end, the unique calculus of common sense under uncertainty.
It started with a gambler's parlor trick, and now it defines reality itself.
And that brings us to our final thought. Think about this as you move forward. What if the normal distribution, the bell curve, is truly the single mathematical signature of the universe? The unified knowledge, dispersing itself into the infinite variety of reality, the information, through infinite divisibility, all while strictly adhering to the simple rules of Kolmogorov's axioms. The universe is predictable, but only probabilistically.
That's a powerful thought, and it confirms that this analysis is an ongoing discussion. We invite you, our listener, to share your own analysis, your sources, and your critiques in the comments. Are we being too optimistic about AI's reliance on these rules? Too critical of classical physics? We really want to hear from you.
And as always, your engagement helps shape the future of this show. If you enjoyed this deep dive, please remember to subscribe on all the platforms. That subscription is critical to helping us unlock funding for high-quality video formats and projects like the Mosaic AI video editor. We're also constantly looking for collaborators to review our content, so if you are a finance expert or a crypto native with a sharp eye for detail, please reach out.
We absolutely rely on that community expertise.
As always, keep searching, keep the quest on.